Welcome to Week 9, Lecture 3, Energy and Systems. This is coming from the first 4 parts of Chapter 13. We're going to talk about work done by external forces, internal energy, friction, and then conservation of energy in a system. So first we're going to look at spring and the earth, block on a spring and the earth. So let's start here where only the block is in the system. Everything else is external. That means there's no potential energy internal to the system because there isn't stuff in the system to reconfigure to cause a change in potential energy. We just have a change in kinetic energy due to the work done by the two external forces, from the spring and from gravity. Now, if instead we had the block and the spring as part of the system now has potential energy internal to the system due to the spring, because we can reconfigure the block and the spring to have spring potential energy. And then the work done by gravity is external to the system. So it changes the energy of the system. And so if instead of the spring, we have the earth in the block in the system, we have gravitational potential energy, but the energy of the system is changed due to work done by the spring. But instead, if we wanted to put it all in our system, that means there's no external forces acting, no external work done, so energy is conserved. So we have a change in kinetic energy, a change in gravitational potential, and a change in spring potential. But the overall energy of our system is conserved. If all of those objects that were exerting forces on the system become part of the system, there's no external forces. So real quick, apologies for this diagram. Your textbook didn't have a diagram, and I didn't want to just talk at you without any visual, so this is what I found. It's not that good. Sorry. So we have a figure skater who pushes off of a wall. We want to think about this with work and energy. The skater themselves is our system. Since there's no other objects in the system, the change in potential energy of the skater is 0. But what about the work? There is force on the wall by the skater, or on the skater by the wall, but there is no displacement at the point of application, which means no work is done. But we know if the skater pushes off the wall, going from 0 velocity to some velocity, that the kinetic energy changed. So where does that change in kinetic energy come from? It comes from a change in the internal energy. And in general, internal energy can be thought of as coming from the kind of microscopic kinetic and potential energies of atoms or molecules in the system, in this case, within the skater. But yeah, so introducing a new idea of internal energy. So now let's look at another situation. We have a block moving across a table with friction. We know, it starts with an initial speed, and then we know that the block will slow down and come to a stop, as long if there isn't any other force making it speed up. If we make our system the block and the table, then there's no external work done on the block, but obviously there is a change in kinetic energy, because, like I said, it's going to start with some velocity, but then over time it will come to a stop. So it means, though, that there must have been a change in the internal energy of the block table system, because there is no external forces acting, so the total energy of the system is constant. So if the kinetic energy decreases, the internal energy must increase. And what this would look like is the surface of the table and the block heating up. So here's a thermal image of a block or box, I guess, being pushed across a surface where there's friction, and you can see that it heats up the surface. So that is also kind of what we're referring to or thinking about as internal energy. Okay, now let's think about a block still, but now it is being pulled across the table with friction, and it's being pulled at a constant velocity. So if our system is just the block, then the force of friction and tension do work on the system. So if it's just the block, the tension and the friction are doing work on the system. And since the kinetic energy is constant because isn't changing because the velocity is constant, and there's no potential energy because the block is the only thing in the system. So the thing that is changing, since we know there's external work being done, we have these two other forces acting, that means the thing changing is the internal energy of the system. So this external work done on the system transports energy into or out of the system. Yeah. So let's investigate this situation with a block attached to a spring sliding across a table with friction. If our system is just the block again, then we have work being done by two sources, the spring and friction. There's no potential energy, but there is internal energy and a changing kinetic energy. The spring force, the work done by the spring force and the work done by the friction force can change the total energy of the system because they are external forces acting on it. Now, if instead we include the spring in our system, there is kinetic, internal, and potential energy, and that is equal to the change in those is equal to the external work done from friction. So now the spring can't change the total energy of the system, but it can change the configuration of energy in the system. So it can increase or decrease and in turn change the kinetic energy and internal energy. But if instead it's all becomes part of the system, the block, the spring, and the table, that means there is no external work done on the system. So the total energy of the system is constant. So here the potential change in potential energy is a combination of both. Oh wait, sorry, no, it's just the spring. So the purpose of going over these two situations and changing the system boundaries around was to show that we can control what is or isn't part of the system, but that changes how we represent things in terms of work and energy. If a force acts on the system but is not internal to the system, then it does work and can change the total energy of the system. But if a force acts internal to the system, then it changes the configuration of energy within the system, but the total energy of the system is unchanged. So when you're doing energy problems, you want to think about what is or isn't in your system in order to tell whether or not energy is conserved and what that looks like. So if the earth isn't part of your system, but there is work done by gravity because your object is moving up and down, then you need to include the work done by gravity within your equation of energy. So this one's a bit shorter than the other ones. It's more about this kind of understanding of and thinking about how these systems work and what changes when you just change the boundaries of those systems.